So the next thing I want to do is I want to kind of refresh you guys on the ideal gas law. So we covered this idea of options. So we probably all remember the ideal gas law, so I'll write it in three different forms here. So PV equals the mass times the gas constant times temperature. Another form, PV equals N times the universal gas constant times temperature. So here I'm talking about mass, here I'm talking about the number of molecules in my ideal gas and the universal gas constant. This is what you first were exposed to in freshman physics. This is what we'll work with more in class. On that note, really we end up using this form most frequently. And so if I divide both sides by m, then I take my volume and I make a specific volume, which is volume per unit mass. And so this form is what we will use mostly throughout the course. But here are three different versions of the ideal gas law. For the sake of this class or this lecture right now, I'm going to be using this form. So I'm going to get back to this in a second, but first I want to talk about entropy versus change in entropy. So I wrote out an expression for what entropy is. Entropy equals Kb times the natural log of omega. And I discussed this water molecule, hydrogen molecule, and hydrogen, atomic hydrogen, and there was different omega. So if I have a system that's magnetic, then I have magnetic degrees of freedom. If I have something that's both magnetic and it's a conductor, then it has, so you can see you can make things more complex and you have more degrees of freedom. But anyways, this is one way to write it. Now the change in entropy. So this is the entropy of the system. And so back to the third law of thermodynamics. If I tell you that there's 1,000 options for my water molecule at room temperature and I cool it down to absolute zero, what is the change in entropy? 1,000 times, natural log of 1,000 times kBT. But I know that S, the number of options at absolute zero, is 1. So I can get a change in entropy, right? The problem is how do you know the number of options when things get really complex? So there's a whole other course you can take on statistical thermodynamics and statistical mechanics to find ways to calculate omega. We're not going to do that. I'm writing this here so you guys have some intuition on degrees of freedom, because when it comes to solving certain problems, you have to think of it in this physics way to understand why the temperature didn't change when I expanded a gas. So sometimes you need to think of it in this way to give you insight on why temperature and pressure. So I'm going to get to the temperature pressure. Before I do that, I'm going to write out another for an ideal gas. There's a couple ways you can write the change in entropy. Now granted, before I had this for an isolated system. So this was for an isolated system. This looks pretty complicated too, right? I have an integral of the reversible heat over temperature, isolated system. Okay, so that's a lot right now. So what I'm going to do is I'm just going to write out two simpler expressions to describe the change in entropy of an ideal gas. And we'll get later in the course, we'll get on how we derive these. But right now I'm just going to do it so the change in entropy is equal to the mass times the heat capacity at constant pressure times the natural log of T2 over T1 minus the mass times the gas constant times the natural log of P2 over P1. So the change in entropy, so when I talked about earlier, I have a gas or a bunch of water at room temperature, and I said there was 1,000 options, and then I cooled it all the way down to absolute zero. So I had my initial state at room temperature, my final state absolute zero. So in that case, T2 would be absolute zero. and T1 would be room temperature, initial and final. And then I have my initial pressure and final pressure. And so just as a reference, delta S equals S2 minus S1. So the change in entropy, entropy at initial state, entropy at final state. So this is one way to write this out. So if I have a gas, ideal gas, and I expand that gas at constant pressure, what happens to the change in entropy? Constant temperature, I can cross this out. I expand a gas at constant pressure, or constant temperature. If I expand a gas, what happens to its pressure inside? I decrease the pressure. Well, I had a minus sign here. So the pressure decreases, I get an increase in entropy. Okay, there's another way to write this. So this was a constant pressure process where it ends up being convenient. So another way to write out the change in entropy is the mass times the heat capacity at constant volume times the natural log, T2 over T1, plus the mass times the gas constant, natural log of V2 over V1. So if I expand my gas, ideal gas at constant temperature, this ends up being 1, right? Initial and final, so this gets crossed out. Now I expand my gas. What happens to my gas? As I expand it, it increases. Say I double, right? I double the volume. So natural log of 2, I can't remember what it is. It's like 1.4 or something like that. But so 1.4 times the gas constant times the mass, that tells me the change in entropy of my gas when I expanded it at constant. So these are just two expressions. So you can see here that this expression says nothing about what the initial entropy was. It just told me the change in entropy. This one tells me what the entropy is, but I need to have very detailed information here. So commonly, there's a bridge between statistical thermodynamics and engineering thermodynamics, and you have to make that bridge. That's why there are several courses on thermodynamics. In this class, we will mainly be looking at changes in entropy. It's really, really, really tough to give you an exact value of entropy. A lot of work goes into that. However, thermodynamics allows you to calculate changes in temperature based off changes in temperature pressure quite easily, which I've demonstrated right here. But tell me how omega changes as I change the temperature and pressure of a system. There's no nice equation like this for these, for omega, that I can plug into here. So back to the states of the system, omega. So what I want to do is I want to give you another pressure temperature analog, pictorial representation of what temperature and pressure is. So we'll go back to the ideal gas, and let's say that, and let's take a diatomic molecule, and it can vibrate this way, and it can rotate, and it has velocities in different directions. So let's just say that this is z, x, and y. So I have velocities or translation in different directions. My molecule can vibrate, okay? And it can rotate. And so with this, I can say something about the state of the system. Now I want to make some pictorial representation of temperature that is related to that. So I'm going to say, if I put some type of so as I increase the temperature, it vibrates more. So if I cool down this room to minus 30 degrees C, I guarantee you everybody in here is going to be like this. Except for some very brave individuals that will be just like, give me the freezing cold. But in general, you are going to, so as you decrease the temperature, that's just an example of vibrational modes, increase the temperature, increase it to really hot, you're going to be doing this. right? So as I change the temperature of my system, I'm going to be increasing kind of the span of my arms at which I vibrate, or this molecule vibrates. I'll be moving around more. I'll be translating all over the room more with higher velocity. So I can represent for some snapshot in time, say 1 nanosecond, a volume associated with this molecule. And I'm going to say that temperature is proportional to some volume. Okay? Some volume. So pictorially, I'm going to represent temperature as a volume of my molecule. That my molecule can... So if it's moving faster in a given snapshot of time, it can occupy more space. If it's vibrating more, so as I increase this stuff, another way to look at this and why I can make this volume justification is I can go back to 1/2 mv squared. That's an energy equals 1/2 kBt. So as you see, I increase the velocity, I increase the temperature. So this is just Boltzmann thermal energy, right? This is kinetic energy. Now I can do the same thing, 1/2 I omega squared equals 1/2 kBt. So if I didn't have any velocity, really it's all of these components equals kBt. And then pictorially, as I increase V and omega and the vibration and all this other stuff, I'm going to increase that volume. So pictorially, I'm just writing temperatures related to the space occupied. Now related to pressure, I'm going to say pressure is proportional to the number of interactions. Okay, so with surroundings. Okay, so given that now this here I didn't say anything about the surroundings for temperature in this case. Now granted, I could put another molecule right here which would change this volume, right? Because if I try to put two people in a chair, maybe your temperature goes up. But in general, that volume is going to change. So there are some boundary. Here I'm just saying for the meantime that it's volume dependent temperature. Now pressure, number of interactions with surroundings. So you can automatically see that as I change the boundary conditions or number of interactions, I'm going to both influence the temperature and the pressure. So let's draw a box. And let's make this box thermally insulated in such a way that all the molecules inside, which I will draw as such, having a volume, when they bounce off this wall, they just elastically bounce off. But if I increase the pressure in a given amount of time, this molecule, in a given amount of time, this one here, can have interactions with its surroundings. So I could look at this pressure as the number of interactions. If I increase this volume, okay, I keep 4 molecules inside at a given temperature. So this represents temperature and the number of interactions with the surroundings. So this molecule can interact with the wall, can interact with this, can interact with that. So I'm going to say that there's some pressure is going to be dictated by the number of interactions with its surroundings. Temperature is going to be dictated by basically how big these molecules are. So if I increase the temperature of my system at constant volume, what should happen to the pressure? Why? Because pictorially, I increase the temperature. And so I do this. And so effectively, in a nanosecond time, whatever time scale you say, as I increase the temperature at constant volume, I increase the number of interactions because it's less displacement, less vibration, motion before I have an interaction. I've defined pressure as the number of interactions with its surroundings. So this represents an increase in temperature. So from here, increase in T at constant volume implies an increase in pressure. So let's just write the ideal gas law. PV equals M R gas T. So I increase the temperature at constant volume. What happens to the pressure? It increases. So this is just my pictorial way of doing this. So let's do another example. So now I have my molecules like such. Okay. And now this is my former boundary. And I'll put in green at t equals 1 minute. So this is my boundary after 1 minute. And I'll put in green what my boundary looked like and this represents at t equals 0. So now I increase the volume and now I didn't change the temperature. What happens to the pressure? It goes down. You can see that as I did this, there's less probability that I have an interaction with the surroundings. For each molecule, the surroundings represent the walls, and so related to the translational degrees of freedom, you could think of it as I made this a cylinder, and I made the cylinder on the order of, this height. You could see that I would only have translational degrees of freedom in one direction. I would change the number of options. I would change the entropy of the system. So there's all this stuff related to it. So this is just my pictorial way of representing the ideal gas law coupled with the Boltzmann way of looking at entropy. So let's look at this pictorially, this one here, and my initial state. And then as I increase the pressure, the temperature, what happens to the number of options? Does it increase or decrease? Increase the temperature at constant volume. Does the number of options increase or decrease? Increase. How do you know? Why? More interactions. Okay? More communication, more options. If I go from higher temperature to low temperature, I decrease the number of options. I decrease the probability or number of the option of communicating with the wall or surrounding in a given amount of time. So in this case, omega goes up. What happens in this case? Volume increase at constant temperature. The pressure goes down. What happens to omega? Pressure goes down. Increase volume at constant temperature. Pressure goes down. Omega. You sure?
If the temperature doesn't change, it stays the same, right?
Look at this one here. Delta S is equal to, temperature stayed the same, pressure went down, so that means that P2 is less than P1. Okay, so this is smaller than that, so I can actually just flip it around and make this a plus sign for P1 over P2. What happened to delta S? What's that? So what happened to that number of options? Okay. So sometimes, you need to do both, is what I'm getting to. Now I can look at this expression, increase the volume at constant temperature. Now it's quite apparent I didn't have to do that flipping a sign. Now let's go back here and let's think. This way, we looked at it as the number of interactions with the surroundings, but the argument here was we had less interactions with the surroundings, but what happened to my number of this molecule can be here, 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 here. As I increase the volume, suddenly this molecule can be here. In this boundary at t equals 0, can this molecule be right here? So you can see how it kind of gets complicated, but you can't just look at number of interactions, you also have to look at number of places you can live, not just the number of neighbors you have where you live, right? So omega went up. I have more translational options.
Excuse me.
Yes?
So omega goes up because of the increase in volume, not because of the decrease in pressure, right?
Well, both. Well, I guess you could argue that it's just the increase in volume. But from that one equation, but yeah, it's mainly because you increase the number of locations.
Okay.
But if I were to say that I increase not at constant temperature, you might get a balance. Yes?
What would our definition of omega be right now?
Number of options. It's anything you can think that's an option. Yeah. So in this case, an option is rotating, vibrating, so there's all the temperature information in options. But there's also, and then when I talked about that, I talked about translational degrees of freedom. And so I gave some velocity. But really there's also this occupational degree of freedom. So there was a translational degree of freedom, but then there's an occupational degree of freedom. So if you go to a neighborhood with only 4 houses, they all might be the same temperature, it might be all Orlando, whatever it might be, but if there's more houses to pick from, you have more occupational degrees of freedom. And so as you increase the volume, I kept all my vibrational and all this other stuff. I actually decreased the number of interactions with surroundings, but at the gain of more occupational degrees of freedom. So if I were to increase the volume with an increase in temperature, I might get no change in entropy. Because the relative increase in size of this might be equal to the relative increase in the change in my boundary volume. Okay. Any other questions on that? I don't know how much time we have. What's that? 11:20. Okay, so that was a lot of what I just covered was a lot of information just kind of on entropy, just kind of getting it, actually just throwing you into the pool of thermodynamics, and a lot of questions you're going to have, and that's fine. Every time you think about thermodynamics, you're going to have more questions and answers. But that's just the way it is. There's nothing wrong with that, right? That's going to be the same way when you're engineering something new. You're going to have more questions than answers, which makes it difficult to keep on getting pay raises. But anyways. Okay, so related to the first law of thermodynamics, what was the equation? Q is defined by delta U minus W. And this W represents work on the system. Not by the system, on the system. We'll get to reasons for that later on. So, this equation, equation 1, is one of many ways to express the first law. There's more ways to express the first law. There's an integral form of the first law, which accounts for internal heat generation, a reaction, which accounts for viscous dissipation. There's a lot of different forms. As you go up and you study more and more complex things, you can get to more and more elaborate versions of the first law. This is the simplest way to start off. It's very limited. So I want you guys to memorize this, but that's when you write out the laws. You'll also, throughout the course, you'll use to solve every problem throughout this course, hopefully the rest of your life. And at first law of thermodynamics, conservation of energy, heat is a form of energy. Everything we deal with obeys the laws of thermodynamics. Everything conserves energy. You have to do energy balance on anything you do. So you will use this, but I'm going to ask you to do it in an energy balance form, not just this. This is the way you want to memorize it, just for writing out what the first law of thermodynamics is, to describe how heat is coupled with the changes in internal energy and work done on the system. But when you solve problems, it's better to write the first law in an energy balance form. So let's draw a system. Here's my system. Okay? And my system has some surroundings. And my surroundings are at a temperature and a pressure. And my system has a temperature, a pressure, a volume, a mass, etc. And it has a boundary, so I can draw a boundary between my system and my surroundings. So we just talked about changes in boundary and how that changes number of options, how that changes temperature and pressure. So I gave you an expression to calculate the entropy. And now I have here the first law of thermodynamics. So if I change the temperature and pressure, so I should have a change in internal energy, right? So you can use heat transfer. So if I add heat and do work and all this other stuff. So I can have energy in to my system, and I can have energy out. And based off the total energy in versus the energy out, I'm going to get a change in internal energy in my system. If I change the boundary conditions, I can dictate what energy comes in and what energy leaves by dictating what comes in and what comes out. I change the change in internal energy in system. Really, it changes the temperature, pressure, volume, and mass of my system. And the change in internal energy is dictated by the changes in these. Okay, so here's a pictorial representation. And let's write the first law in energy balance form. So I have energy in minus energy out equals the change in internal energy in my system. So when I say internal energy, that's everything, all the forms of energy inside my boundary. I define the boundary, all the forms of energy inside. Internal. This represents energy transferred from my surroundings to my system, energy in. This defines the energy transfer from my system to my surroundings. So if I have a balance between energy in and energy out, what happens to if energy in equals energy out, what happens to the change in internal energy in my system? It doesn't change, it's zero, okay? So this is an energy balance form. Now coupled with this, I can write energy in is equal to the heat in plus the work in plus the energy associated with mass in. And I can write the energy out is equal to the heat out plus my work out plus the energy associated with mass out. So I can plug this into here and that into there, and I guess I can do that. So let's just do that. So I have Q in plus work in plus energy associated with mass in minus heat out, work out plus energy associated with mass out equals the change in internal energy in my system. So let's say that let's try to get it back to this form up above. What can I cross out? What do I need to cross out to get it to that form? No mass. Q in and Q out, I cross out. Work in. So then if I subtract this from both sides, yeah. So if I do this, that means the change in internal energy, Q in, work in. Work in, work on the system. This is just a simplified version of this, taking into account that I'm only considering work in. So if I put a minus sign here, then I have what? Minus work heat in, which is equivalent to heat out. So if I have a plus sign here, that means it's minus work in, which is equivalent to work by the system. So this just takes into account all the sign conserv, right? Positive means heat in, positive means work in, work on the system. So I can write it like that. Where Q, energy due to heat, energy due to work, energy mass, energy due to mass transfer. Yes. Okay. If I consider each one of these having mass and a temperature, right? Each one of my pens. There's an entropy associated with each pen. There's an internal energy associated with each pen. I take my pen, I put it in a bucket. That's my system. What do? I take mass of a given energy and I add it to my system. What am I doing? I'm increasing the internal energy in my system. I'm increasing the internal energy in my system. I'm increasing. There's an internal energy and entropy associated with each one of these pens. That's my mass in. If I take my bucket and I start removing, so I have an entropy and an internal, so my system decreases associated with mass leaving. It's entropy and internal energy, right? I just took out something. If I take out enough, it's a vacuum. What is the internal energy of a vacuum? Okay, that's kind of maybe a philosophical question. But you get the general idea. So if I take out all the mass, what is the entropy of nothingness? So there's an entropy and internal energy associated with all the masses I add. And so here is the first law in energy balance form, talking about how heat, mass, and work are coupled to the change in internal energy of my system. Of course, for all that to happen, I have to have forms of energy crossing a boundary. Without a boundary, I cannot define a system because I don't know the difference between the surroundings and the system. Without a boundary, I don't know whether heat can cross. I can have a boundary where there can be no heat transfer. So you can change the boundary conditions. So if I have a boundary with no heat transfer, then I can cross these out. What is a boundary with no heat transfer? That represents an adiabatic system or an adiabatic process. I have a process where there is no net heat transfer in and out. So if I look at that, I get rid of heat in and heat out. So I can cross out this. So let's just write it, adiabatic. I can have heat in an adiabatic process, but it has to be balanced in that process. It has to be balanced by equal amount of heat out. So Q in minus Q out is 0, so I can cross this out. So what do I get? Work in is equal to the change in internal energy of my system. That's exactly what I wrote in words in the first law of thermodynamics. In an adiabatic system, Q is equal to 0. So Q is equal to 0. That means I can't have any heat in or heat out, right? So that's 0, and then I just have the change in internal energy is equal to the work on the system. Work on the system is the work into the system from the surroundings. So I suggest you memorize how to derive all this stuff in the laws, right? At some point there'll be quizzes on it.